Wronskian. In differential equations, when we have to show a set of functions linearly independent, we use Wronskian. So for let me find Wronskian for a 2 by 2 determinant and 3 by 3. So when we have two functions, let's say case 1, one solution is y1 and another solution y2, and when we want to show these two are linearly independent, we can basically just find Wronskian of these two. Let me denote by W equals, it will be a 2 by 2 determinant y1 y2 in the first row and their derivatives in the second row. So find y1 prime and y2 prime. Now we evaluate this 2 by 2 determinant. We just multiply this diagonal y1 times y2 prime and minus, we multiply this way, y1 prime y2. Okay, like if we have two functions, let's say cosine t and sine t, and if we are asked to find Wronskian of these two functions, then Wronskian will be cosine sine. Okay, in the second row, now we find their derivatives. Derivative of cosine is negative sine, and derivative of cosine is, sine is cosine. Now let's multiply. This is cosine, cosine, cosine square minus, this way is negative sine square minus, and negative sine square means plus sine square t, and cosine square plus sine square is 1. Okay, in application, when we do this in differential equations, when the Wronskian is not equal to 0, then these two solutions form a fundamental set of solutions. Okay, let's do for 3 by 3, and we can go for 4 by 4, I mean 4 solutions as well, but let's just do up to 3. So y1, y2 and y3 are solutions. Okay, now we want to find Wronskian of these 3 solutions. That will be then a 3 by 3 determinant. So y1, y2, y3 in first row, their first derivatives in second row, and their second derivatives in third row. So this is, I meant y1, y2 double prime, y3 double prime. Now we need to evaluate this 3 by 3 determinant. If you have taken a linear algebra course, then you already know how to evaluate. Otherwise you can do the following. Just, I want to expand along first row. So this will be y1 times, just delete the row and column containing this y1 and write down the 2 by 2 determinant. So it will be y2 prime, y3 prime, y2 double prime, y3 double prime, y1, then y2, due to the position this will be negative, so plus minus plus, and y2 times, now we delete the row and column containing y2 and write down the 2 by 2 determinant. So y1 prime, y3 prime, y1 double prime, y3 double prime, and finally plus. Okay, the third is y3, it's plus minus plus, by location this will be y3. We just delete the row and column containing that element. So y1 prime, y2 prime, y1 double prime, y2 double prime, and we know how to evaluate 2 by 2 determinant. So this will be then y1, we just multiply this way, y2 prime, y3 double prime, minus this way, y2 double prime, y3 prime, minus y2 times this way y1 prime y3 double prime minus y1 prime y1 double prime y3 prime plus y3 this way y1 prime y2 double prime minus y1 prime double prime y2 prime. Okay, I just expanded along first column, but you might be depending on this, sometimes it's easier to go along, expand along first column. Okay, then plus minus plus, or some of you already know how to do. There might be other ways, there are other ways to evaluate. Okay, so here's an example. Find Wronskian of 1 et and e to the negative t. Okay, so the Wronskian of these three functions, in fact in our case these three will be solutions of a differential equation. 1 et e to the negative t, they are first derivatives, so 0 et e to the t negative means negative that. Second derivative 0 et negative and positive e to the negative t. Now we want to expand this, and it's easier to go along first column, unlike what I did earlier, because 1 0 0 we don't have to even do for 0 0. Okay, so expanding this will be 1. Now we delete the row and column containing 1, that's e to the t minus e to the negative t, e to the t, e to the negative t, minus 0, but everything becomes 0, so I don't have to do anything, and 1 does not count. So basically we have a 2 by 2 determinant here. Let's multiply this way, e to the t times e to the negative t, same base, we add the exponent, so e to the 0 minus this way plus minus negative, so plus e to the t, e to the negative t is again e to the 0, because t minus 2 0. E to the 0 is 1 plus 1 2. So this is how we find Wronskian. And in differential equations, when these functions are solutions, Wronskian not equal to 0 means these solutions form a fundamental set of solutions. Okay, final